I'm very especially pleased to announce the next speaker, Viviane Clay, because she's not only my co-worker, but she's also, in my opinion, a very enthusiastic, creative, and brilliant researcher. And her research is focused on teaching neural networks a robust and meaningful understanding of their input by analyzing how they represent information under different learning conditions. She's going to talk about learning semantically meaningful representations through embodiment. Please, let's give a warm welcome to Viviane.
Hello everybody, thank you for the very nice introduction. I'm glad that Tim Pietzmann gave this great talk this morning because he already motivated a lot of what I'm working on. So basically in the past years there's been an advent of deep learning, and many people have applied deep learning to many different problems and have shown great performance in all kinds of domains, outperforming humans and other methods. But although it was in the beginning slightly biologically motivated, not so many people have stayed close to trying to keep these networks biologically similar or training them how humans or animals would learn. And I'm trying to look a little closer at this. So in recent years, some people have shown some flaws that these deep neural networks have. So although they perform very well in very many domains, they sometimes make mistakes. And of course, humans also make mistakes, but they make very different mistakes than humans would, which kind of shows that they are not a perfect model of the human brain or an animal brain. So just to show some examples, in 2015, they have shown if you add some very specific noise to an image, just very slightly multiplied by 0.007, you can trick a network to classify this picture, which obviously shows a panda, as a gibbon with 99.3% confidence, which is not a mistake that a human would make. You wouldn't even see the change between the two pictures. And then a more recent paper here looked at natural images. Nothing was done to these images that trick most of these image classification networks. So for example, in these two images you see a squirrel, and here the squirrel is misclassified as a sea lion. So now if you look a little closer, you can kind of see where this comes from. So the water surface is black and reflective and maybe a little like the skin of a sea lion. But a human would never say this is a sea lion because the shape is just completely different. And same here, you have it is classified as a rocking chair. You can kind of see this fence structure looks a little bit like some rocking chairs would, but you would never say there's a rocking chair anywhere in this picture. Different example here. Here the network seems to look more at the context. So there's a hummingbird feeder in the picture, but no actual hummingbird. So it still says there's a hummingbird because just in many images with hummingbird feeders there are also hummingbirds in the picture. And now that there are bees, it still says this is a hummingbird. And here you see that the mushroom was classified as a pretzel. You can also see kind of low-level features of a pretzel around here, like the curvature, texture. And people have shown that these image networks have an over-reliance on local image features like texture and don't really consider global features like the overall outline of an object. So how can we deal with this problem? I propose a solution that basically looks at how these networks are trained. So there are two main differences you can make out if you compare how you train a fully supervised neural network compared to training a human child, namely supervision and embodiment. So for one, the child doesn't have some adult following him around all the time saying table, 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 chair, 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 chair. They mainly just kind of explore on their own, look around, and hugely unsupervised learn during the first years. And the second thing, embodiment. They interact with their world They move things around, they move their head around, see things from different perspectives. And if you look at how neural networks are trained, it really makes sense that they make such mistakes and that they rely on texture, because if you just get a 2D pixel input of objects, how are you ever supposed to figure out things like object-background relationships? A child can just see this object and can then look at it from a different perspective and notice the object moves more than the background, for example, and have a depth perception. It can pick up an object and move it around, learn that it's distinct from the table, stuff like that, that a neural network has almost no chance to really figure out just from static images. So the idea is really, it has already been proposed a while ago, that experience is not something that happens in us, but is something we do. So it is obvious that for action we need perception, but that also for perception and a true understanding of the world we need action and interaction with the world to make sense of our perceptions. So for my experiments, I take a deep neural network. Here you can see in blue. It's not super deep, but it is a neural network, and I train it in a reinforcement learning setup. So we have a virtual environment which provides the network with some input. In this case, it is a 3D maze environment, and the network gets RGB camera images, as well as a small vector which tells the agent how many keys the agent is holding, how much time is left, and the level the agent is in. And these observations at time point t go into the network, get processed, the network calculates it encodes this input, and then uses this encoding to decide on the next actions. These actions then get sent back to the environment and determine the next observations that the agent gets. So there's really a closed loop between action and perception. So the observations at time point t determine the actions, which then determine the next observations. And also the environment is randomly generated. It can have random lighting conditions, random textures on the wall, so the agent can really not memorize the path or just look at the RGB color statistics, for example. Also, just to point this out, this network is extremely small, so it has about half of the number of neurons that a jellyfish has. So we often compare neural networks to human performance, but forget that they have a lot less complexity. So even though the performance is not perfect, it is pretty impressive for being such a small network to solve a complex vision task plus motor control task. So now I hope that this video works. Here you can see the environment. So this agent runs through the tower. This is the trained agent. There are normal doors, like the green doors that you just have to walk through, and these yellow doors bring the agent one level up. The time is running out, as you can see over here. And sometimes the agent has to pick up a key to open this key door. Later on there are some puzzles that I introduced, and these blue spheres that you saw earlier, here was one, they give the agent some extra time. So this agent currently can run up to level 10. Let's see how fast this. Can't see the mouse here. Oh well. The whole environment is has very sparse rewards, so there's very little supervision for the agent to learn. The agent gets a reward of 1 when he walks through one of these yellow doors and gets 1 level up. And other small events like walking through normal doors or picking up these blue spheres give a reward of 0.1. Overall, the agent only gets a reward in less than 2% of the frames. to show something else, but I don't know how to skip forward in this video because I don't have control over it. I can show it here. Yeah. Let's see. It doesn't want to. You can just see it in this picture. Here you can see the encoding of the middle layer of the agent. So basically, this layer here that is circled in red with the corresponding activations at this frame. So the agent sees this, it goes through the network, and the network activations look like this. This is from the image input, and this is from the vector input, basically telling the agent how much time is left and which level the agent is in. It's a bummer it doesn't work with the video right now, but you can see like some of the neurons are active, some are a little less active, most of them are not active. And if you look at the overall statistics over one run, here you can see in how many percentage of frames the neurons were active, and you can see that especially for the visual encoding, most neurons are active in at least some of the frames, but very few neurons are active in like all of the frames. So none of them are active in all frames. 7 neurons are active in more than 40% of the frames, and overall there are 15 active neurons on average in each frame, which is about 3% of the neurons that are available. So we can see that the agent has learned a very sparse encoding of the high-dimensional sensory input with a wide variety in the activation patterns. And this is something that people have also seen in biology, so they have seen this in insects, mammals, humans, rodents, that they encode high-dimensional sensory input in a sparse way. Just as a comparison, this is the agent before he was trained. There you can see if you just put it through a random network, it represents the information very redundantly. And there was no regularization or anything enforcing this representation. It was just that this kind of representation is more robust to noise and makes it for the agent easier to decide on the next action based on this kind of representation. So now we want to see if this representation is also meaningful and has some meaning encoded in it and isn't just random. So here I correlated so basically the representations were clustered using k-means clustering into 6 clusters. And the idea is that k-means clustering kind of looks at patterns in the high-dimensional space and then puts the single data points into buckets that should be kind of similar and also in their meaning similar. And when you correlate the cluster assignment with the action that was performed at this time point, you can see that there's a positive and for some clusters negative correlation with the specific action. This is, for example, for the action forward and turn right. You can see that this cluster is positively correlated with the action, this one is more negatively correlated. And comparing to a random agent, there's just no structure in the clusters at all. And if you look at the 6 most prominent action combinations, you can see, so every cluster has like a distinct action combination that has a very high correlation here. So for example, here in cluster 2, backward and turn right is very strongly positively correlated. Here in cluster 1, forward, camera right, turn right is strongly positively correlated. And the magnitudes compared to the random agent are much higher. So here you can see the sum of squares of the correlations. There's a huge difference. And this is just for actions. If we look at some semantic content, so for example, doors, you can see that, for example, here in this clustering, doors are very strongly correlated with cluster 5. And I can just show you all the frames that are in cluster 5. You can see it's like a lot of frames with yellow doors, some green doors, some also just have the blue spheres in there. So in general, a lot of rewarding experiences that are in the frame of view of the agent, but the agent hasn't reached this reward point yet. And now you can also see this encoding in motion. So basically, with respect to image content and actions, we can see some meaningful differences within the clusters. And now I will show this in a more visual way. So this is from a random agent. If you take these activation patterns, they have dimensionality 256, so it's really hard to visualize that. So I projected on a two-dimensional space using TSNE. Which basically tries to preserve the distance relationships in high-dimensional space and projecting to a lower-dimensional space. And in this plot, it's from one single run, so 5,000 frames, the agent runs through the tower, and it is colored by the action that was performed at this frame. And right now, I can't make out any structure in this. I don't know if you can, but we can see a very clear difference. If we now train this agent and then cluster again the representations, it looks like this. So you can see that the agent has learned a very action-oriented encoding of its visual input. So you can make out some pretty clear clusters of the different action combinations in here, but also some content. You can see that it's kind of clustered. So here's, for example, the door that leads to the next level, the yellow door. And you can see within the respective action combinations, they kind of fall close together. And if you, for example, look at these 3 frames, they all happen at different points in time. So this one is very early, this one is more in the middle of the training. They all have different illumination conditions, so here it's more green light, more yellow light, more dark. So the RGB values are kind of different, the time is different, but they are still perceptually similar to this agent. So the agent seems to encode, for one, actions and action-relevant objects, disregarding action-irrelevant factors such as illumination or the texture of the wall and things like that. So that was the main point. If you like to, for example, explore this interactively and just click on all the points and see what the corresponding observations are, you can scan this QR code and visit the website with some more interactive and fun results. And also, if you like to send me a message or connect with me, use some contact information. And I would also like to thank my supervisors for some really helpful feedback and input, Peter König, Kai-Uwe Kühnberger, and Gordon Pieper. And now I'm open for your questions.
Questions?
I have two related questions. So one is if you have thought of perhaps better baseline to compare your trained agent rather than a random agent. Like maybe there's like a, I don't know, I haven't thought about it, but maybe there's an obvious alternative which is more reliable than just random, which would be a way to check how difficult the task is for the agent to get trained. And then the other question, what I think is related, is how, if you have a way to characterize like what is the level of the features that the trained agent relies on to focus on the task. If you can say that there are really like high level features here, it is really understanding the environment, or maybe it's just picking up very low level features, like for example color
so to your first question, I've thought about what would be the best baseline to compare it to. And for a good comparison, two criteria are basically that the encoding should have the same dimensionality and it should be based kind of on the same input. So a random agent is naturally presented itself because I could, let me just go back here, I could use exactly this structure here, same operations that are applied to exactly the same input, and then get the same dimensionality of an encoding. I also want to compare it to agents that were trained under different conditions, so for example with no rewards, just curiosity, or more sparse rewards, but this is still work in progress. Another idea that we talked about earlier would be to train an autoencoder, simply just the visual input in, encoded state, and then another deconvolutional network to reconstruct the input. And I will look at that, but also don't have the results here. For your second question, if the agent really uses higher level or lower level features of the input, as the environment is randomly generated and the lighting conditions and color conditions and also the texture of objects can randomly change, I don't think the agent can rely too much on just simple color values, for example. But of course, it can still look at kind of lower level features like just the outline of a door or so. But for example, if you present the agent with a door that he never walked through before in a different color, he will try to walk through the door.
So if no one goes, I'm not good. It's a very technical question. Are there ReLU units in the convolutional bit of the network, or what's the nonlinearity that you use?
I use the swish function. It's a new activation function that was introduced and supposed to be very good.
When you say neurons are not, or units are not active, does that mean below threshold, or how do you define not active?
Yeah, so I was thinking about how to best define this, and I finally settled on if the activation is below 0, they are not active.
Very useful. Can you take us please a bit through the loss functions that you have here? So you have policy loss, value loss, reward, all these are captured different parts of what is good for the what is good performance for the agent, I guess. So how did you come up with this part of the design for the network?
Yeah, so I didn't come up with this part. This is basically proximal policy optimization, which is one of the state-of-the-art reinforcement learning or deep reinforcement learning algorithms. So for this part, I basically used an existing implementation of this algorithm. Yeah. And for the loss, it basically learns using this reward, and then also some smaller things like what's the entropy over the action probabilities.
Thank you.
Also, thanks from my side for this very interesting talk. In the beginning, you motivated what you were doing by looking at errors in picture labeling, basically. And I'm fully on board with the motivation, but now maybe a challenging question would be, how do these action-oriented categories that this agent developed ultimately help improve something like picture labeling, which would be a linguistics task, according to your point of view?
Yeah, so this is all still work in progress, and one of the ideas is now to take this encoded state and use it for example, classification, and compare it to just fully supervised feed-forward model doing the same task, like for example saying, is there a door in the input or not, and seeing if it is more robust to noise adversarial examples and things like that.
More questions?
mentioned shortly that you also used curiosity as an reward. Can you say a little bit more about that? How you implement curiosity?
Yeah, so I didn't show any results from that, but this is a very interesting concept, I think, where the agent basically gets some intrinsic reward. So he has an additional task. Besides just navigating, he also has to predict the next observation based on the current observation and the action he's performing. So it is some kind of predictive task. And the more wrong this prediction is, the more reward he actually gets for the reinforcement learning part. So basically the prediction part tries to minimize the loss between the prediction and the actual next frame, but the agent itself and the action he decides on are trying to maximize this loss. So just thinking about it, this basically means that the agent is actively seeking novel experiences. He's actively performing actions that could lead to unexpected observations. And in order to do this, there are like some side effects. So in order to get more novel observations, he has to survive for longer. He has to be able to navigate and not just run in a wall and stay there. And this can actually get an agent like this to learn to navigate this environment without any rewards from the environment itself. So that's a really interesting idea that I'm currently exploring, and the network is currently training, but it takes a really long time to learn.
More questions? Okay, then let's thank again our speaker for this great talk.